All right, for our first illustration of the fundamental theorem of line integrals, we'll look at question 3. It says compute the line integral of the vector field f, where f is 3 plus 2xy, comma, x squared minus 3y squared, and sees the path parameterized by the vector function r of t, which is equal to e to the minus t sine ti plus e to the minus t cosine tj, and t varies from 0 to pi. Okay, so I have a sketch of our path here, and I first want to highlight that when time t is 0, we're going to be up here at the point 0, 1, just plugging 0 in for the uh, component functions there for r of t. Now when t is pi, we're then going to be down here at the point 0, comma, minus e to the minus pi. All right, and the other thing to notice is that this field f is the same field from question 2, part A, and we found a potential function for that field. It was this function phi, which was 3x plus x squared y minus y cubed plus a constant a. All right, so the fact that f is equal to the gradient of phi implies that the line integral of f over this path c is equal to the line integral of the gradient of phi over that path. And now the fundamental theorem of line integral says that this integral right here is just the potential function phi evaluated at these two endpoints, and then I'm taking the difference. And when I do that, I'm going to get this value 1 minus e to the minus 3 pi. Okay. Now, two comments here before we finish. The first is that this constant a, okay, much like what you see in Calc 2, if you're computing an indefinite integral, you're always told to include a plus c. But then when you go to compute a definite integral, since when you take the difference, the constant plus c will drop out, you're usually told to just omit it. Well, same thing here, right? When I take this difference, this constant a would just drop out. So you just as well could set a to 0 if you like. The other comment I want to make is that if I were to go ahead and compute this line integral using the techniques from the last section, this would be pretty messy, okay? Because I'd be substituting these component functions in for x and y, and then I'd have to go about and compute the line integral element, ds, right? I mean, which is doable, but that's going to be a mess. And so if you were to carry that all through, it would be quite a bit more complex than what we just did here. This is actually really simple, okay? And in the very last thing I want to say is that because we have this potential function, okay, we integrated from this point 0, 1 to this point 0, comma, minus e to the minus pi along that path. But see, if I were to mix things up and say, no, now I'm going to integrate over, say, this path. Okay, what would be the value then? It would be this, right? Because it would be exactly the same calculation, because uh, all the expression you see right here cares about is the value of the potential at the endpoints. So, all right, that's a good place to stop. I'll see you in question 4.